Greetings everyone, my name is Dr. P. Pavan Kumar. In this video, I am going to explain you the Einstein coefficients and relation between them. This is a topic in the chapter of lasers in advanced engineering physics. Now, we'll see that. So the contents here are Einstein coefficients and relation between Einstein coefficients we are seeing in this video. Now first we'll see Einstein coefficients. To understand these Einstein coefficients, we must have a basic knowledge or we must know the basic definitions which were there in another video. You can go through that. So just I'm revising it here. So first one is absorption. So the ground state particles absorb energy and they will move to the excited state by taking a energy here. So that phenomena is only called absorption. And now if we see the mathematical, if I represent it, the probability of particles moving from state 1 to state 2, that is E1 state to E2 state, depends on what factors? The number of particles available in the lower state, and another one, the amount of energy I am giving here. So without energy they cannot excite, and another one, without number of particles here, without particles they cannot excite. So that depends on number of particles in the lower state, and that also depends on the amount of energy we are giving there. So that's P12 here represents the probability of particles move from state 1 to state 2 is directly proportional to N1. And that's also directly proportional to rho v. Rho v is the energy density here. Now combinedly I can write P12 is equal to N1 rho v, and by removing this proportionality I will write a constant B12. So B12 is called Einstein coefficient of absorption. So B12 represent Einstein coefficient of absorption, and this is the standard method. We must use always B12 only for the Einstein coefficient for the absorption. Now we'll see the another Einstein coefficient which related to emission. Again I am considering E1 energy state. N1 is the number of particles in E1 state, and E2 is the excited state, and N2 is the number of particles in excited state. Here after a lifetime, the particles will come to lower state E2 to E1 automatically or spontaneously by emitting a photon. This phenomena is called spontaneous emission. Now mathematically we will represent it in the form of equations, right? The probability of particles moving from E2 to E1 depends on depends on only one factor, that is number of particles available in the excited state. So P21, that is probability of particles move from state 2 to state 1 by spontaneous emission, that is a representation here, is proportional to N2, number of particles in the excited state. Here we are not using any energy for the de-excitation, so that does not depends on the external energy we supplied for the de-excitation. Now by removing this proportionality we will write a constant A21. This A21 is called Einstein coefficient of spontaneous emission. I'm repeating, A21 is the Einstein coefficient of spontaneous emission. Now we'll see the another phenomena, that's what stimulated emission, which is the principle in laser. So I consider E1 is a ground state, E2 is the excited state. E1 consists of N1 number of particles, E2 is the N2 number of particles. Now if I give energy for the de-excitation, this will stimulate the excited particle to the lower state. As a result, 2 photons gets released, and these 2 photons are in same phase. This phenomena is called stimulated emission. Now the probability of particles moving from state E2 to E1 depends on number of particles available in the excited state, that is N2, and that also depends on the amount of energy you are supplying for the de-excitation, that is rho v. Now we can write combinedly P21 stimulated is proportional to N2. So that is probability of particles move from state 2 to state 1, it's not 21, state 2 to state 1 by stimulated emission is proportional to N2. And that's also proportional to rho v, energy density, and combinedly we can write N2 rho v, and by removing this proportionality we will write a constant of B21, that B21 is the Einstein coefficient of stimulated emission. So these three are the Einstein coefficients for the absorption, spontaneous emission and stimulated emission. Now we'll get the relation between these coefficients. So for that, I'm rewriting the equations. So that's absorption. P12 is equal to B12 N1 rho V, where B12 is Einstein coefficient of absorption, and emission is two types of emissions are there. One is a spontaneous and other one is a stimulated emission. So P21 spontaneous is equals to A21 N2. A21 here is a Einstein coefficient of spontaneous emission, and B21 is the Einstein coefficient of stimulated emission. These three equations we have taken from our previous explanation. Now for any system which is in equilibrium, what happens is number of particles moving up will be equal to number of particles moving down, or we can say upward transitions are equal to the downward transitions. That's absorption is equal to emission, or I can write absorption is equal to spontaneous emission plus stimulated emission. Now the probabilities I am equating here, P12 is equal to P21 spontaneous plus P21 stimulated. Now using our previous equations 1, 2, 3, just to substitute 1, 2, 3 in this equation, then that leads to this one. N1 rho V B12 is equal to N2 rho V B21 plus A21. Now take out rho V common. So by that N12 B12 minus N2 B21 I'll get, and is equal to N2 A21. Now take this entire term to the denominator here. So I can write this N2 A21 by N1 B12 minus N2 B21. Now take out N2 common from this and cancel out with the numerator. And here in case of lasers, almost all the excited particles will come to the lower state by stimulated emission only. So as we are discussing in lasers, we can write B12 is equals to B21. And once I'm telling you, this is applicable only in case of lasers. If you take a normal light, this is not valid. So as we are in lasers, we can write B12 is nearly equals to B21. Now according to Boltzmann distribution law, we can write the ratio of the numbers N1 by N2 can be written as exponential E2 minus E1 by KT, where K is a Boltzmann constant and T is a absolute temperature. Now E2 minus E1, anyways a photon gets released, so that can be written as h nu. So by substituting all these things in the previous equation, we can write rho V is equal to A21 by B21, 1 by exponential h nu by KT minus 1. Now, according to Planck, the radiated energy can be written as 8 pi h nu cube by c cube into 1 by exponential h nu by kt minus 1. And this refers to energy, and this also refers to energy. Now, compare these equations 8 and 9. By that, we will get A21 by B21 is equals to 8 pi h nu cube by c cube. And this is the another relation between Einstein coefficients. And the previous B12 is equal to B21, that is equation number 7. And now the equation 10, both are taken as the relation between Einstein coefficients. So this is an important relation in case of lasers. So thank you very much, and happy learning. Thank you.